We're getting ready to start our last unit here, which is going to include sections from Chapter 11 and Chapter 12. We start out with Chapter 11, which is going to talk about a little bit more on series. We're going to specifically talk about what's called a power series to start with, because we're going to get involved with taking our series and turning them into functions of x. So a power series is going to include x. It's going to look in general like x minus a to the k times c sub k, where c sub k is a real number. And typically, c sub k is going to include all of our kind of usual suspects. It could have something like maybe k factorial over a tower function, or maybe this could have maybe a 3 to the k. Um, really, this is where all of our sort of chapter 10 series would end up. So we're basically tacking on x minus a to the k, where a is a real number and x is a variable. So we're going to have then these coefficients, the c sub k's, and a will be called the center of our power series. So we have this x minus a. We're going to end up with, as it says down here, some sort of value. If we let x be equal to a, right, this whole thing collapses down to 0. And for sure, when we plug 0 in here, we'll have just a sum of zeros. So this will definitely converge. What happens is a is going to be the center then where we have 0. And we'll usually have some x values to play around with near a, so that when we take our x minus a, we still get a convergent series. And when x sort of falls too far away from a, this x minus a gets too big, and when we take it to the k power, it ends up diverging. So what will happen is we will have an interval of convergence that shows the x values in which we actually get convergence up here. The radius of convergence is going to be the distance from a to the outside of our radius. So that's going to be capital R. So that's the distance from the center to the boundary of the interval. How do we determine the interval? Well, if we have x to the k, that's where our center is 0, or x minus a to the k, where our center is a, we'll use pretty much the ratio or the root test. So that's going to be our most typical uses: ratio test, root test. Occasionally, if we are lucky, we can maybe get some sort of geometric series involved, but usually just these two. And it says, furthermore, because these terms could be positive or negative, we have to use absolute convergence. So we always start with testing for absolute convergence. So by theorem 10.21, if we determine the value for x for which the series converges absolutely, we have convergence. So here's our theorem. We have a power series centered at a. It converges in one of 3 ways. So either x doesn't matter in the convergence, in which case the interval is all real numbers and the radius is infinity. That means our c sub k's converge so well that x really doesn't matter that much. Or we could have, there is some real number, capital R, that gives us our radius, so that the series converges absolutely for x minus a less than r. And this is going to mean negative r less than x minus a less than r. It means that we actually have some radius of convergence. Right, x will be less than r plus a, and it'll be greater than a minus r. And so that will be some finite number. The radius of convergence is r, and we'll have some sort of interval. We do need to check the endpoint. It says here the series may or may not converge at either of the endpoints and must be checked. So we will have to check also when we get this case in particular whether we converge at the endpoints or diverge. And lastly, we have the series converges only at a, because c sub k may not converge at all, in which case the radius of convergence is r equals 0. And so the only value that will actually work is if we have a minus a and we get the whole thing collapses down to 0. So we'll go ahead and take a look at a power series. We're going to go ahead and figure out how do we determine convergence, where do we converge, what values of x make this happen. So we always want to start by looking at absolute convergence here. So we're going to start by taking the absolute value of our terms, of our integrand here. And we'll note that k factorial is always going to be positive. So we can go ahead and take that out of the absolute values. And so we'll just have x to the k. Right, and we could actually move a little bit further than this. Right, x is able to be either positive or negative. So that is really the only value that we need to take the absolute value of. This is now always positive because k is always going to be positive, right? We have an exponential here anyway that can't go below 0 as long as our base is positive. So here is the series we're looking at. We're going to go ahead and run it through a ratio test. So we'll find r. That's going to be the limit as k tends to infinity. Remember, we put the k plus 1 term in the top here. And we put the kth term in the denominator. And so we'll go ahead and flip and multiply the denominator. So we have x to the k plus 1 times k factorial over k plus 1 factorial, and then we have x to the k. And then we'll split these terms up. Right, that absolute value of x to the k plus 1 becomes absolute value of x to the k times absolute value of x. In the denominator, k plus 1 factorial turns into k plus 1 times k factorial. So we get some cancellation that goes on here. And we end up with the limit as k tends to infinity of the absolute value of x over k plus 1. Which as k tends to infinity, right, the absolute value of x acts as a constant in terms of k. We could actually even take that out if it's more comfortable. Times the limit as k tends to infinity of 1 over k plus 1. And this guy goes to 0. And then times absolute value of x is 0. So what happened is, this is our r, which is less than 1. And in fact, it doesn't depend on what x is equal to. No matter what x is, our r is always equal to 0, which is less than 1. So this guy will always converge. And so for this first one, I'll go ahead and write down this concept. Any value of x would result in r equals 0, which is less than 1. So the series converges under the ratio test for all x, or for any x in the real numbers. And so I will be defined to be equal to, these are the values of x that work, and we say the colon and the equals defined to be equal to negative infinity to infinity. And so r would be equal to infinity. I'll just say thus. And so there is our interval, our radius, that's what we were asked for. And in fact, since we have all real numbers, there are no endpoints to check. No endpoints to check. Because we can't really plug in negative infinity, infinity, those are not real numbers. So we just are left with that. So there's an example of the c sub k's converge so well that x to the k cannot possibly sort of undo that. The factorial grows so much faster than anything we could really put in an exponential. So we look at another one here. This one, we know we see the x minus 2 to the k. That means that we have a center at 2, which means guaranteed this guy would converge when x is equal to 2. And so we just want to find out, is there more? How much more? So again, we start out with the absolute value over the entire thing. And we'll kind of go through and pick off which pieces actually need the absolute value and which pieces are always positive. Which pieces do we get rid of? We have an alternating series here, so that would go away under the absolute value. And so we can continue to look here. 4 to the k is also always positive. And again, the kth power doesn't necessarily affect the sign so much as the base does. So if we have x minus 2 in the absolute value, now this is always positive. For this guy, we actually see that we have a kth power in the numerator and the denominator. We'll go ahead and bring that out. So this is now k equals 0 to infinity. This is absolute value of x minus 2 over 4, this whole thing to the kth power. So looking at that, we can see that the best case for this is going to be the root test. So we'll go ahead and look at rho. That's going to be the limit as k tends to infinity. It's an equal sign here. Limit as k tends to infinity of the kth root of x minus 2 over 4 all to the kth power. So that kth root and kth power will cancel. We get the limit as k tends to infinity of x minus 2 over 4. There are now no k's involved. So this is equal to what the limit value is. So this is what rho is equal to. It does depend on x. So we have to remember, for convergence, we want 0 less than or equal to rho less than or equal to, or sorry, less than 1. So we want 0 less than or equal to absolute value of x minus 2 over 4 less than 1. So what we'll go ahead and do is multiply all three sides here by 4. 0 less than or equal to x minus 2 in the absolute value less than 4. And when we take a look at this section here, absolute value is, of course, going to be greater than or equal to 0. So we'll just focus on this. We take away the absolute value by setting this in between negative 4 and 4. We add 2 to all these sides here. And so we get, for sure, the values that'll work. So we can say the series converges absolutely for x in between negative 2 and 6. So x being an element of this interval from negative 2 to 6. And possibly at our endpoints at x equals negative 2 and x equals 6. We must check. And we think, why is that? What happens when x is equal to negative 2 and 6? Back up in this context. When x is equal to negative 2, we get negative 2 minus 2, absolute value is 4 over 4. That's equal to 1. So that's an issue, right? When rho equals 1, that's inconclusive. Inconclusive. There we go. And so that's why we have to specifically check our endpoints. The way we check our endpoints is we plug them in. If x equals negative 2, then we have the series here. If we look back at our original, we plug in negative 2. Our series would end up being negative 1 to the k. And then let's do negative 2 here. Minus 2 to the k over 4 to the k, which is equal to k equals 0 to infinity. We've got negative 1 to the k, and now negative 2 minus 2 is negative 4 to the k over 4 to the k. Which, if we go ahead and bring out all the k powers here, this is equal to k equals 0 to infinity. We have negative 1 times negative 4 over 4 all to the k power. And this is equal to 4 over 4 to the k, which is 1 to the k. And so finally we get that this is the series from k equals 0 to infinity of 1. This diverges. So this is a series which diverges, and we have to think why. Well, it certainly will just get bigger and bigger and bigger, right? That's the divergence test that causes that to fail. By the divergence test. I guess we should capitalize that, huh? So -2 is not going to be included in our interval. So we go ahead and test our other endpoint. If x is equal to 6, then we have k equals 0 to infinity, -1 to the k, 6 minus 2 to the k over 4 to the k. And so we go ahead and simplify a little bit. -1 to the k, 4 to the k over 4 to the k, which is equal to, well, it looks like we get -1 to the k. And this diverges also. Again, by the, we could talk about it by the divergence test, right? If k is even, then we get +1 as our limit. If k is odd, we get -1. So the limit doesn't exist. Or we could just say a divergent geometric series with r equal to -1, right? That's another case for divergence here. So we'll also leave out 6. So the only part of our interval that works is the interior here, from -2 to 6, exclusive. So therefore, I will be equal to the interval -2 to 6. And so r, oops, get my definition dots in there, is defined to be, well, we'd have to figure out what is the distance from our center to one of these points. So 2 ways to figure that out. We could either just find the halfway point between these guys, or half the distance between these guys, rather, which is 6 minus -2 over 2. So half the distance there, 8 over 2, which is 4. Or we could go ahead and actually look for our center here, which is 2, and then look at just the distance from maybe 6 to 2. Either way. So there's our interval and our radius of convergence. So this is one case where the rest of our series here, this -1 to the k over 4 to the k, is not kind of strong enough on its own to cause convergence. We actually do need x to help out. And when x is too big, we get divergence here. So now we go ahead and look at a third example here. Again, start by taking the absolute value. And by following kind of the same idea as before, we get that k factorial is always positive, so we'll just go ahead and confine our absolute value to x. And we'll go ahead and run the ratio test. And you can probably imagine that there will be some pretty quick work here. K plus 1 factorial, absolute value of x to the k plus 1 over k factorial, absolute value of x to the k. So that's the limit as k tends to infinity of k plus 1 times k factorial times absolute value of x to the k, absolute value of x, over k factorial, absolute value of x to the k. So those guys cancel, and we're left with absolute value of x limit as k tends to infinity of k plus 1, which is infinite. So we think that there's probably, it looks like, oops, this should be r. Looks like r is equal to infinity. Isn't that no matter what x is? Well, the thing is that this test only works if we have positive terms here. And the only time we wouldn't get a positive term here, since we've taken the absolute value, is when x is equal to 0. So this entire test is provided x not equal to 0, which is A in this problem. Because our power series would, of course, converge if x was equal to 0. The whole thing would be 0, and we would just get zeros across the board. Just 0 added to itself an infinite number of times. So when x is equal to 0, as I said, we get k factorial times 0 to the k, which is just k equals 1 to infinity of 0, which is 0. So our interval of convergence only contains 0. So we'll go ahead and make a singleton, which is a set containing only one object in it. And our radius, since there is only one object in here, is 0. There's no space between the center and anything else. So that's our third option. There's no x that's sort of small enough to contain the divergence of this factorial unless we just use 0. All right, so this one here tells us to use the ratio test, and so we'll go ahead and do that. We have to take, again, the absolute value of our integrand here, or sorry, our summand. Wrong one. There we go. And apply the same sort of pattern that we did before. So 3x minus 2 gets the absolute value, and root k is always positive. So that is the absolute value we're looking at. We'll go ahead and use the ratio test. R is going to be the limit as k tends to infinity. We'll go ahead and put our k plus 1th term up top. And our original kth term on the bottom here. Flip, multiply. So 3x minus 2 in the absolute values. Put that root k next to it. And then same absolute value on the bottom, except this time just to the kth power. Then root k plus 1. So we get the limit as k tends to infinity. We split this guy up. And our issue being that we actually cannot do anything with that square root. So that's kind of just have to stay the way it is. I want to make sure to extend your absolute value bar so it doesn't look like 13x minus 21. So those guys will cancel. And so we've got the absolute value of 3x minus 2. Since that doesn't involve k's, we can bring it out of the limit. And we've got root k over root k plus 1. And so we'll go ahead and bring the root out of that whole fraction there. So the limit as k tends to infinity of root, and the whole k over k plus 1 is now involved in that root. We can actually bring the limit inside the root now. So we have k over k plus 1. And now this is L'Hopital's rule here. I guess it was back here, but this is going to be a one step. So we'll go ahead and have 3x minus 2, and then take L'Hopital's rule, limit as k tends to infinity of 1 over 1. And so we just get absolute value of 3x minus 2. So we want this guy to be less than 1. That's our intention. So we'll go ahead and set that down here. This is what we want. Obviously, again, it's going to be greater than or equal to 0, guaranteed, since it does have that absolute value. So we'll go ahead and focus on this part of our inequality. 3x minus 2 is in between then negative 1 and 1. We add 2 to both sides. Divide by 3. We got 1/3 less than x less than 1. So that's going to be our interval of convergence is going to include 1/3 to 1. But we have to see what happens at 1/3, what happens at 1. So we check these endpoints. Firstly, if x equals 1/3, we'll go ahead back up to our series up here. 1/3 times 3, we get 1. So we've got k equals 1 to infinity. And we'll go ahead and we've got 1/3 times 3 is 1, minus 2 is negative 1 to the k over root k. And so we have to figure out then, what exactly does this do? Right, this is an alternating series. And in fact, it's one that we saw in the alternating series. In the alternating series section, we actually used this exact one before. So real quick reminder, we'll go ahead and look at the associated function. Remember, we look at it without the alternator there. And we need to look at a couple things, right? First, we look at sign chart. We need to make sure everything's positive here. So we've got an issue at 0. We'll go ahead and check to the right here. F of 1, that's 1 over root 1, which is 1, that's positive. So we have positivity. We need to check to make sure that it's non-increasing. So we look at the first derivative. So f prime of x would be 1/2. And we put our root x in the bottom here. Sorry, it should be negative 1/2. And then x to the 3/2. And again, we sign test. We have an issue at 0. We test to the right here. So we've got f prime of 1 is negative 1/2. That's negative. So we have decreasing. So we have positive, we have decreasing. The last thing we check is the limit as k tends to infinity of everything but the alternator. And of course, that goes to 0. So this series converges by the alternating series test. And so we include 1/3 in the interval of convergence. So that's a real quick test of alternating series that shows that. So next, we check if x equals, we test the other endpoint, 1. So we have k equals 1 to infinity. We'll go ahead and look up here and check. We've got 3 times 1 is 1, minus 2 is 1 to the k over root k. And that's just going to be equal to that 1 to the k is just 1, so 1 over root k. And this is just a p-series. It doesn't alternate. And in fact, it's a divergent p-series because p equals 1/2, which is less than 1. So we don't include 1 in our interval of convergence. So our interval of convergence would then be defined as 1/3 to 1, including 1/3, not including 1. And our radius of convergence, I'll again just sort of take the difference between the two and divide it by 2. We get 2/3 over 2, and so we get 2 over 6, which is 1/3. So there's our interval and our radius. Important thing to note is that whether the endpoints are included or not, the radius is going to be the same, because the radius only cares about where the endpoints are, not whether they're actually included or not. All right, so now that we've seen a couple of different power series kind of by themselves, we'll talk about what happens if you start combining power series. So again, what we're trying to do here is we're trying to start injecting these x's into our series because we're going to want to start defining new functions based on series. And we're going to figure out how these functions are related to functions we already know. So it says here, a power series defines a function on its interval of convergence. So where I is, that's actually where this guy up here is a function. When power series are combined algebraically, new functions are defined. So say we have two different power series, one with c sub k as our coefficient and one with d sub k. Say they both converge absolutely on an interval. Say they both converge on the same interval, in fact. So if we add them together, we actually get a new function on I. They converge absolutely to the addition of these functions. So we're actually going to say here that c sub kx to the k converges to f of x. Say that we actually know what it converges to. That converges to a function that we can write down here. And we have our other function there. So when we add the two series, we add the two functions on I. We can also multiply by a power, so it's a little different than usual. If we have a power series where we have x to the m times our series, we can actually bring that x inside since it's not dependent on k. And it converges to x to the m times our function. So this is something that's not necessarily typical when we start talking about these normal, I guess, function descriptions, right? Usually we talk about maybe multiplying by a constant. Now we're actually able to multiply by a power of x, which is pretty cool. We also have composition, but it's a bit weaker. There's not a whole lot more that we can say. We can't say the usual composition, in fact. So our inner function has to look like a constant times x to a power. And moreover, it has to be a positive integer power. So we can actually plug that into our power series, and it's the same as finding f of h of x or on I. Power series can also be defined as products and quotients, but as you can imagine, since we're adding an infinite number of terms, when we're also multiplying and dividing, that's really hard to do. This also applies, this whole theorem applies to stuff that's centered, maybe not necessarily at 0. We have this x to the k, which means we're centered at 0. It works if we change the center. Property 1, it works exactly the same. Properties 2 and 3, we have to have sort of the center of our power series has to be the same as the polynomial we're multiplying in. And here we have to have the same sort of changed center. This has to be x minus a to the nth power. So why does this actually help us here? Well, if we have, say, a geometric series converging to a function, right? This is x to the k. We know by our rules for geometric series that we have a over 1 minus r. That's equal to our summation here. We can apply that involving x's. So we have x here as our r. So we have our first term as 1. We put that up there. We have 1 minus r, which is x right there. So what can happen is now we can use that to find the power series and the interval of convergence for if we take this guy and multiply it by, say, a power of x. Right, so we use one of those properties up here before. This function here is actually x to the 5th times 1 over 1 minus x, which means according to the properties we just looked at, we can actually take that x to the 5th and multiply it by our series, which means that we can just show this to be x to the k plus 5 in following along with that. So now we want to figure out where does this converge? What is our interval of convergence? So the interval of convergence, if we look back up here, it should be the same I. So all we need to do is show where the original series converges, and the new series should converge there as well. So that's another helpful result that comes out of that previous theorem. So for a geometric series to converge, we know that the absolute value of r must be less than 1. And the thing is, with geometric series, when r is equal to 1, we get divergence. There's no inconclusive values. So there are no inconclusive values for r. So there are no endpoints to test. So that's kind of nice. Here we have absolute value of r being less than 1. R is equal to x. So we have absolute value of x less than 1. So negative 1 less than x less than 1. So our interval of convergence was relatively easy to find here. We have negative 1 to 1. And so our radius of convergence, well, our center is 0. So we go 0 to 1 is just 1. So here's our power series and our interval of convergence. I guess we weren't asked for the radius, but we found it anyway for free. There we go. So we were able to find that using that original series just because we have this kind of nice properties of power series. So we can actually take this even further now and start talking about, well, what happens if we try to differentiate or integrate power series? So some properties of polynomials carry over to power series, others don't. A polynomial is defined for all values of x. Power series is only on the interval of convergence. So if we just restrict to the interval of convergence, most properties will carry over. So let's talk about integration. If we have a function defined on a power series on its interval of convergence, then we know that f is continuous on I. That's what we get from this theorem. F is continuous on I. And we can differentiate or integrate term by term. And the result is f prime of x or the integral of f. So that's going to work on all of I, where we have that plus c, that's an arbitrary constant. So that's cool. We actually get that we can take our power series and look at the function it's related to, and to find the integral or derivative, we can actually just use the power series to find that. So here's the problem. The endpoints might get lost. So it says theorem 11.5 makes no claim about the convergence of the differentiator integrated series at the endpoints of the interval. The statements about term-by-term differentiation say two things. We have convergence on the interior of the interval of convergence. Interior meaning not necessarily the endpoints. Interior is no endpoints. It says the theorem claims more than convergence. The differentiated and integrated power series converge, and not only do they converge, but they converge to the derivative and indefinite integral of f. So that's pretty cool. If we have a function that is difficult to integrate or differentiate, but it has a nice power series, we can just use that route instead. So let's go ahead and look at how that differentiation might work. If we have our coefficient times x minus a to the k, and we know that it converges on some radius, then we'll call it a function. It'll converge to a function on that radius. So anywhere inside the interval of convergence, we have a function. It has derivatives of all orders inside that interval of convergence. So we can take derivatives forever. We can obtain the derivatives by differentiating the original series term by term. So if we take this guy and we just think, well, in general, what if my function was, let's call it g of x here for a second. And say we're not even looking at the summation. We just look at c sub k x minus a to the k. Well, if I wanted to take the derivative, right, I would do the power rule. I would take k, bring it down, and I'd have k minus 1 as my power, and I'd have to do, right, the chain rule. I just have 1 here. So this is my result. Right? So if we plop a series in front of it, it will give us the same exact thing. You see that we actually have k times c to the k, x minus a to the k minus 1. One thing that we notice that's a little different than expected, though, is when we are looking at the series, we get k equals 0 to start with. We have k equals 1 on our first derivative. Right? So let's think about why that is. If we plug in k equals 0, the first term is c sub 0, x minus a to the 0. X minus a to the 0 turns into 1. So we have a constant plus c sub 1, x minus a to the first. Oops, x minus a to the first plus c sub 2, x minus a squared, and so on. So that first term is actually a constant. So when we take the derivative, the first term goes away. And so that's why we start at k equals 1 now. Right. And now the first term of this guy is going to be a constant. So if we take the derivative again, the first term goes away. We start with k equals 2. But again, we take the power, bring it down, decrease the power by 1. And so you can see that since our power series will always look like c sub k, x minus a to the k, our derivatives are going to be super straightforward. And they converge at every interior point on the interval of convergence. So we get a nice consistent derivative. It'll always look the same. The only things that'll change are what c sub k is actually equal to, and we'll have an a in there. If we look at integration, it works pretty much the same way. If we have our integral, our function here, and we're looking on the interval of convergence, then what we'll do is the inverse power rule, right? We increase the power by 1 and divide by the new power. That's what we have here. And that'll converge for everything on our interior. And we add our constant back in to get our full indefinite integral. Right, so instead of changing the our index, our starting index, we'll go ahead and just add our plus c like usual. So that's really cool. It changes our derivatives and our integrals into very consistent objects here. So we'll go ahead and look at x to the k over k. And we'll go ahead and try to figure out what then would be the derivative of that guy. Right? And it's going to be pretty much exactly what we would hope it to be. So what we'll do, excuse me, is we'll go ahead and think about what would happen if that summation wasn't there. Right? We would take the power down and decrease the power by 1. All right, so we'll go ahead and put the series back there, increase the index by 1. We'll go ahead and check to make sure that's necessary first. Let's go ahead and plug that in. K equals 1. Let's go ahead and figure that out. We've got x to the first over 1. Actually, that first term does include an x because we didn't start with k equals 0 like back in our example back here. So that is something you're going to have to be careful of. We're not starting at k equals 0, so we'll go ahead and keep it at k equals 1 because that first term isn't a constant. And so we can cancel a bit here. And so we get x to the k minus 1. And so we think about what that's equal to. Let's go ahead and keep going here. We got x squared over 2 plus x to the third over 3, and so on and so forth. So we think about the term-by-term differentiation there. When we do that, we go ahead and we get our first term here. If we take the derivative, is just 1. And we look here. Plug in k equals 1. We get x to the 1 minus 1. That's 1. Take the derivative of this guy. We get, let's see, bring down the power. We get x to the first. Plug in 2. We get x to the first. Bring down the power. That cancels. We get x squared. Plug in 3 here. We get x squared. And so we can see if we take the derivative of our general term, or if we take the derivative term by term, it's the same thing. And so we'll end up with the same result. So that's going to be our, first derivative. And so that's going to be our result, is the first derivative looks like that. So very simple to find. And now we integrate. If we want to try to integrate, again, I'll go ahead and write down some markers here, some of our terms. We've got x to the k over k. So when we write that down, we've got x over 1 plus x squared over 2 plus x to the third over 3 plus x to the fourth over 4, and so on. So we should be able to take the integral of both sides and work out just fine here. So we're going to take the indefinite integral with respect to x of both sides. That should be our integral of f of x. And when we do that, on the left side here, we'll go ahead and integrate this guy. And the only reason that this is possible, that we can actually switch these signs around, is because we know that this guy does converge here for our interval. So since we know this converges, we can actually take the integral and move it inside. And so here we get x squared over 2 plus x to the third over 2 times 3 plus x to the fourth over 3 times 4, and so on. This is 1 times 2 here. And I write that down just so we can see this in a sec here. We've got the integral from k equals 1 to infinity of, we increase the power by 1 and divide by the new power. And then we just add c at the end. We'll add c here. So let's think about, do these match up? Plug in k equals 1, we get x squared on the top. 1 times 2. Yep. Plug in k equals 2, we get 2 plus 1 is 3. 2 times 3. And so it does match up perfectly. So this is going to be then our integral. All right, so again, integration works just as well as taking the derivative does. We just need to make sure, just be careful that we've got a matchup between our index and our terms here. So why is this useful? Well, let's go ahead and look at a power series representation for a function in particular and an interval of convergence. So say we want to find that representation, give the interval. When we do that, we're actually going to be able to do all kinds of stuff with this function that we wouldn't be able to before. So say we take inverse tangent, for example. Inverse tangent is something that we can definitely take the derivative of, but it's very difficult to integrate. So what we'll go ahead and do is we'll figure out what is maybe some way we can write this as a power series, and we would be able to integrate by integrating the power series. So to find the power series representation, we're going to have to figure out, is there some way we can make this look more familiar, right, as a power series? So let's go ahead and take a look at the first derivative. If we take a look at the first derivative, we get 1 over 1 plus x squared. Right, that's the derivative of the arctangent. This looks a lot like a representation of the sum of a geometric series, if we can just write the bottom as a subtraction. There we go. Right, this looks like a over 1 minus r. So here, a equals 1, and r equals negative x squared. Which means that we can rewrite this using our geometric series rules from k equals 0 to infinity of a times r to the k. And so we can rewrite this then just by arranging some terms. This is negative 1 to the k times x squared to the k. Right, if we just split that guy up. And so this is from k equals 0 to infinity, this sum, negative 1 to the k, x to the 2k. All right, so let's talk about what does this series look like, first of all. Plug in 0, we get 1. Plug in 1, we get negative 1 times x squared. Plug in k equals 2, we get positive number here, and then x to the 4th minus x to the 6th plus x to the 8th, and so on. So that's our series. That's what it looks like term by term there. Let's talk about convergence. So to converge, we need absolute value of r less than 1. Right, this is a geometric series. So all we need is absolute value of r less than 1. R is negative x squared. So we go ahead and look at then absolute value of x, and then we've got it squared here. That's always going to be positive. Really, all we need to do is get rid of the negative. Right, x squared is always positive, and so we just need to get rid of the negative. X squared is less than 1. That's going to be good enough for us here. So if x squared is less than 1, it operates the same way as an absolute value, right? That means that x is in between negative 1 and 1. So that's going to be our our interval of convergence then, -1 to 1, for f prime of x. All right, so to find the inverse tangent of x as a power series, we're going to have to integrate. We'll integrate this guy. So we've got our power series for the derivative. We'll integrate it. So let's say that we are on the interior of I then. We'll go ahead and integrate term by term, which means that we'll go ahead and add 1 to the power. We'll get x to the 2k plus 1 and divide by that new power. And then we'll have k equals 0 to infinity, and we'll add on a c to the end. So here is our inverse tangent then written as a power series. So the issue is, remembering back to our theorems here, makes no claim about the convergence of the integrated series at the endpoints. So once we take the integral, we might have convergence that pops up at one of these endpoints. So if we want to get the interval of convergence, we have to test the endpoints. So integration may cause endpoints to be included. So we must check. So if x equals 1, we look at our series up here. K equals 0 to infinity. We're looking at the inverse tangent here is this guy. So we have -1, then to the k, 1 to the 2k plus 1 over 2k plus 1. And 1 to any power is just going to be 1 here. So we have the series from k equals 0 to infinity of -1 to the k over 2k plus 1. This is an alternating series, so we're going to need to check using the alternating series test. So we'll go ahead and make a function relating to the non-alternating part. So we need to do, first off, our sign test. So we have to figure out where is the asymptote going to be. 2x plus 1 equals 0. We got 2x equals -1, so x equals -1/2. So that's where our hole is going to be in our graph, in our domain. And so we have this whole section that we can plug in. So let's go ahead and plug in g of 0. That's 1 over 1, which is positive. So we have that our terms are positive. Next, we look at the first derivative. We have -1 over 2x plus 1 squared, and then take the chain rule there. So we change that to a 2. Go ahead and erase that, make that look a little prettier. All right, so we'll go ahead and same process. We got no new issues because the numerator is just a number. So we've got -1/2 here as our whole. I'll go ahead and plug in 0 again. G prime of 0, -2 over 1 squared. So that's -2. That's negative. So we've got positive, we got non-increasing. All we need now is the limit as k tends to infinity of, we've got 1 over 2x plus 1. Sorry, should have a k in there. K plus 1. And that's going to be equal to 0. Therefore, the series converges by the alternating series test. So we say that 1 is included in our interval of convergence. Next, we test -1. So we've got k equals 0 to infinity, -1 to the k, And then we have negative 1 to the 2k plus 1. 2k plus 1 for any integer is going to be odd. So this guy will just be equal to negative 1. And so we get k equals 0 to infinity of negative 1 to the k plus 1 over 2k plus 1, which looks suspiciously like this guy back up here. It's the same argument. So we say similarly, the series converges by alternating series test. So negative 1 is also in I. And therefore, I is defined to be equal to negative 1 to 1 inclusive. And so that's our interval of convergence. And we'll go ahead and box our series as well. Right, actually, we don't need the plus c even either. We can figure out what c is equal to. Plug in 0, we get 0. Plug in 0 here, we get 0 plus c equals 0, so c equals 0. So that's going to be our result then.